All right, let's talk about how to find minimums and maximums whenever it comes to motion, solving for mins and max and mins. So here's kind of an example question. A ball is thrown directly up in the air with initial velocity 24 meters per second. What maximum height does it reach? Now, if you were just going to solve this using standard kinematics, you would immediately go to v equals v naught plus 2ax minus x naught. Right? You'd set your final velocity to be 0. Your initial velocity would be 24. Acceleration is the acceleration of gravity, negative 9.81. Notice we're calling down to be negative, up to be positive, right? And your x naught would be 0, and you'd be able to solve for x directly using one of the kinematic equations. But what if you're not allowed to use one of the kinematic equations? Or more importantly, what if you're given a different equation besides the kinematics that describes the motion of something, like in another example problem we're going to do? What do you do then? So if you have a function and you need to find the min or the max of it, you'd first off, number one, take the derivative of the function. So if you need to find a maximum point or a minimum point for a function, you take the derivative. Then you set it equal to 0 and you solve, okay? The last thing you got to do is you need to plug that maximum point back into the equations, back into the original equation, and please plug it back into, please plug the endpoints back in if you're given endpoints to make sure that they aren't the maximum or the minimum. More information on that idea with endpoints here on the next slide. Let me show you what I mean here though with this problem. Really, the motion of this ball is defined according to position by this kinematic equation, right? X naught v naught t 1/2 a t squared. So whenever I plug in my known values, 0 for x naught, 24 for v naught, negative 9.81 for a, so 1/2 times negative 9.81 gives me that negative 4.905, I have this equation for the position of the ball. That would be the defining equation for the position of this ball that I would end up having to write. But how do I maximize this function, a function of position according to time as indicated right here? How do I maximize this function? Well, I take the derivative of it. So let's go ahead and do that. All right, so let's start doing the derivative here. 24t to the first power, so that 1 gets multiplied down. 24 times 1 is 24. And then t to the first power, so the power minus 1. That gives me 1 minus 1, 0. T to the 0, so the t completely goes away. Plus, negative, now that t to the second power right here, that 2 gets multiplied down, turning this negative 4.905 back into a negative 9.81 t, and that 2 now up in the exponent, minus 1, leaves me with a 1. And the derivative of a position time function is velocity. Now this should look incredibly similar to another one of your kinematic equations. Let me just write this up top just so you can see it quite easily. V equals v naught plus at. That's another one of our kinematic equations, by the way, how we get between those two. All right, so that's step one, take the derivative of the function. Now, let's actually set it equal to 0 and solve it through. And I come out with a time 2.4 seconds. Now, that's the time where the ball reached the maximum height. Okay, that's how we find the max. And that should make some sense to you because notice, whenever you take the derivative of a position time function, you get velocity. And whenever something is at its maximum height, we already had discussed, the velocity equals 0. So thus, the idea of setting equal to 0 and solving for time should make a lot of sense. But now you have to look at this and go, that's not what I was asked for. I was asked for what maximum height does it reach? That's okay. We know at what time it reaches that maximum height. So now all we need to do is take this and plug back into my equation up here for position. And I come out with a maximum displacement of 29 meters. It might have been wise of me, though, instead of using x here, x of t, to use y of t, because we are moving in the y-axis. Also, another note for you, whenever I substitute back in, I did not substitute back in the number rounded for the number of sig figs, 2.4. I used the full decimal 2.44, so on and so forth, from my calculator, just to make sure I was coming out and then with the right answer, and then rounded for sig figs once again at the final answer. You might also be thinking, hey, it's so much easier if I just come and use one of our kinematic equations. I can solve directly for it instead of having to write kinematic equation for position, take the derivative of it, and then substitute solve for time, right? Set it equal to 0, solve for time, and then take that time and substitute all the way back in to that original equation. That just seems crazy. Yeah, it does whenever you could use your kinematics, right? But you're not always going to have you're not always going to be able to use your kinematic equations. There'll be times that a different equation describing object's motion exists. There'll be times where acceleration isn't constant. Acceleration is changing according to some equation. And those are the circumstances where you need a little bit more power. You can't just go with, here's an equation, substitute in. You need the actual math behind it, which the derivative is. So once again, just a quick reminder, if you ever need to maximize something or find the maximum or the minimum of something, whether it's I have the position function and I want to find the maximum position it reaches, or maybe it's I have a velocity function and I want to find the maximum velocity that it reaches. Doesn't matter what the function is, take the derivative, set it equal to 0, and solve for the time that it occurs at. Then to find out what the actual maximum is, plug it back into the original equation, but you're also going to need, and you'll see this here in a moment, to plug in the endpoints too, if you're given endpoints, to check to see if those were actually the highest or the lowest points instead of what you solved for. All right, let's define some parts of graphs here for you. Endpoints are simply the points between which you're operating. So, for example, 0 right here, and maybe the problem also says, and we stop all the way on the other end somewhere around, I don't know, let's say 20 seconds, if this time is in seconds as it's listed there. And those are your endpoints. You will need, if you're solving for maximum and minimums, to plug those endpoints back in to see if they're going to give you your maximums or your minimums. For example, if you were looking for, if you had a function like that described this motion here with the graph, you would actually need to, and you were looking for the minimum position you were at, you would need to plug the endpoints in because the endpoints are the minimum position. It's where x equals 0. And no other spot on this graph would end up giving you the minimums if you were solving for it. There are other graphs where you'll need to plug the minimums in, and I'll show you that. Let's go ahead and do it down here. So down here, if you took the derivative of this graph at the bottom, if you took the derivative of this graph and set it equal to 0, you would end up with 3 points. This, and this as either maximums or minimums. Now you wouldn't know what was a maximum, what was a minimum, until you actually plugged them in to see how tall they are. This is a relative maximum, a relative minimum. This is the highest maximum. But this relative minimum down here isn't the lowest point on the graph. It's not the lowest point of the function. You would have to plug in the endpoints that you were given. 0 to 20 seconds is, let's say, how far the car was operating. That's what we're operating inside of. You'd have to plug the endpoints in to actually see that the minimum position was 0 according to that function. You also have your maximum points. That's the first derivative. You take the function, you take the derivative of it, you set it equal to 0. Now, if you're in a position time graph, up here's the spot where, notice the slope of a position time graph is velocity, and so this is the spot where velocity equals 0. X time graph, velocity equals 0, first derivative for maximum. Inflection points. Now, inflection points are where, if you're in an X time position time graph, the acceleration changes. We are accelerating up, and then we start decelerating down. That's the second derivative. If you think about it, this is where the acceleration is going to equal 0. To move from some positive acceleration, right, to eventually a positive deceleration, same thing as a negative acceleration, right? You have to pass through 0, coming from positives to negative. That's the inflection point. That's where the curve changes from, let's say, going up to curving back off flat. That's the second derivative. Once again, shows where acceleration equals 0, and you have inflection points all over the place, wherever the curve changes. Well, looking at this bottom one, I have endpoints. I have a relative maximum, a relative minimum, the maximum, and here are some inflection points in between them as they change, as the curve changes, as the acceleration goes up and then it becomes deceleration, and then we accelerate down negative and then we decelerate negative back off to a stop. So just a few terms that you need to be familiar with. I'm going to work an example problem for you where the kinematic equations don't actually work. So I have a subway car, and the subway car travels between these two stops, stop 1 and stop 2, and it's described by this equation here. Now, why do you need this equation? Well, because the subway car, we're actually looking at the entire motion of it, and the acceleration changes during it. For the first half, as the car is going this way, according to this equation, the car is accelerating, and then somewhere, in fact, right at the halfway point, it decelerates all the way to the second stop, and so then it starts decelerating until it stops at spot number 2. Then, on the way back, let's choose a different color, it accelerates back up, all the way then to coming back to stop 1, and it starts decelerating at the middle. That's just how this function ends up working. So this is a good example of where the position equation just isn't simple. I've got changing accelerations all throughout. So I'm given an equation, and it asks me, please find how far the stops are away from each other. So if you think about that, if I set this as x equals 0, the car is going to go up to the second stop at some final far x. This should be x equals question mark, and it will be the maximum position away it goes. Then the car starts returning back down to 0. Maybe we could sketch a quick graph of this idea. Graphing it isn't always necessary, but a graph of this would look, let's get a good deceleration, and then acceleration, deceleration, and it levels back out. And so down here is stop 1, and then up here is stop 2, if this is a position in meters, time, let's make it in seconds. Graph here. So it comes all the way up to stop 2, and then it comes back down, accelerating, decelerating. So there's an inflection point right there, acceleration, deceleration, and same thing over here, inflection point, accel, and deceleration. So we can't just use kinematics. We actually have to use calculus for this one. Now, if we can calculate where this maximum point is, what is the max of this? Wherever that maximum position is where stop 2 is at. So let's write our equation down and then take the derivative of it. All right, since we're trying to find the maximum point, so now that we have the derivative, let's set this equal to 0. All right, and so now I'm solving. I went ahead and I factored out a t. Notice I have t cubed, t squared, and t. So I factored out a t here, leaving now squared, single, and no t. And you'll notice now this is a nice quadratic, and I can use the quadratic equation. So standard here factoring, now I've got two factors, right? So I can set each of them individually to equal 0. So t equals 0, or 0 equals t, and 0 is going to equal all of this other stuff. Here that is. If you want, you could also factor out a 1 over 15 from this. I'm not going to worry about it. I'm just going to go ahead and solve from here. All right, so now I've plugged into the quadratic equation, all the numbers that I'm going to possibly need. Now I just let my calculator do the work. So now I have 3 times t equals 0, t equals 8, and there's a little point here, 8.0 seconds, and t equals 16 seconds. So let's actually put units on there. 3 times that this car has 0 velocity. And whenever it's at 0 velocity, it's either going to be an endpoint or it's going to be our maximum or minimums in the equation. Now think about the physics of this. This actually makes sense. The car is starting out over here at stop 1. Whenever you initially let it go, it has a 0 initial velocity. Then it accelerates up here in the black, accelerates up, and then here in the middle, right, it starts to decelerate down where it stops logically, right? V equals 0 over here at stop 2, right? So it started out, V equals 0, and then it accelerated and decelerated to stop 2, and then it has V equals 0 over there. Then it comes back. Now we're following the green, accelerating up, decelerating down, back to its original position, where once again at stop 1, V equals 0 again. It comes back to a stop. So this should make logical sense. Here's where we started, right? Here's the start. Here's over here at stop 2, and now we're back at stop 1. We're going to check ourselves though. Okay, here's what we're going to do. We're not solving for the time, we're solving for how far are the stops away from each other. So we're assuming that we're right in this logic that t equals 0 is the starting point, t equals 0.80 seconds is at stop number 2, and at 16 seconds it's come back to stop number 1. That's very logical, but we need to double check ourselves, and we need to solve for the displacement. So what we do is we take these 3 times and we plug it back in to our original equation. X of t equals 1 over 60 t to the 4th, blah, blah, blah. So we're going to actually plug it back in there and solve for x. We have 3 times to plug back in and solve for x. Whichever one is the largest, which we're assuming is going to be at 8.0 seconds, whichever one is the largest, that's going to be how far away stop number 2 is. All right, so I rewrote the position equation, and I'm going to start out with my first time, t equals 0, substituting that in for my t's to see at what position, whenever I substitute in 0 for this time, and this time, and this time, so substituting in, whenever I do that, what position was the car at t equals 0? And I quite obviously come out with at time equals 0, substituting zeros for everything here, I'm at 0 meters. Now I'm going to do it again for 8 seconds. And I find after 8 seconds, the position of this cart is now 68 meters away. So lastly, I need to do the same thing again just for 16 seconds. And whenever I plug 16 back in, I come out once again with the position at t equaling 16 seconds is 0. Now, technically, I should have, instead of putting this little notation down here, I should have just put 0 in here and 8 in here and 16 in there for that notation. But that shows the final answer. The distance, our initial assumption was right. This is the start. This is when we come back, right? And this is at stop 2. Right? So this right here, 68 meters, is our final answer.